Okay, we were left with a difficult question. We were asked to look at nitrogen dioxide and to see if we could figure out how to put it together. Nitrogen has 1, 2, 3, 4, 5 electrons. Oxygen has 1, 2, 3, 4, 5, 6 electrons. So right off the bat, we can see that if we make a double bond between one of the oxygens and the nitrogen, then that oxygen gets to have 8 electrons. So that seems like a good thing to do. And then we said, well, if we take the other oxygen and do this, then, well, some things are right, some things are wrong. Now, nothing's ever going to be right because there's an odd number of electrons here. That central atom has 5 odd number of electrons, and the oxygens around it have 6, an even number of electrons. So you're never going to make anything balance. But a little bit of logic says this nitrogen's left over with 2 electrons right here, and oxygen is more electronegative than nitrogen. So maybe the oxygen should have electrons. That nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. So it looks kind of right. And this oxygen looks right, but that oxygen clearly is wrong. It has 7 electrons. And there's never going to be a way that we're going to get around the fact that something is going to have an odd number of electrons. But there is another way. There is a way that we give the oxygen, the most electronegative atom, a closed shell. Did anybody have a stab at this? It is difficult. And it does involve doing something that we haven't seen before. The oxygen doesn't go here. The oxygen goes here. Yeah. It has 1, 2, 3, 4, 5, 6 electrons of its own. And then that nitrogen gives 2 electrons to the oxygen. We had defined a covalent bond. What was our definition of a covalent bond? 2 electrons shared between 2 atoms. Here's an electron, there's an electron. We shared between 2 atoms. Okay. How is that different than here's 2 electrons and I'm sharing them between 2 atoms? This, finger waving, you might have to pay attention to the fingers. This and that, technically the same thing. Okay. Now, when we noticed this, we gave this covalent bond a special name. It used to be called a dative bond, D-A-T-I-V-E, but it's now called a coordinate covalent bond, which is why I have told you don't call them non-bonding electrons. To say that these are non-bonding pairs of electrons is the wrong title, because these electrons are bonding. They are responsible for bonding, and yet the books won't change the name. So most people call them lone pairs of electrons, which is the old-fashioned name, waiting for somebody to fix the new name being non-bonding pairs of electrons. Well, it's bonding. In a coordinate covalent bond, what happens is both electrons come from the same atom. Okay. This is not strange. This might look familiar to you. This is the net ionic equation for every acid-base reaction. You just wrote a lab report on the net ionic equation for acid-base neutralization, right? Oxygen has 6 electrons. 1, 2, 3, 4, 5, 6. The hydrogen adds another one, and then there's a negative charge. That negative charge is an additional electron from somewhere. How many electrons does an H plus have? No. How many electrons does H plus have? How many electrons does an H atom have? 1. If I turn this atom into an ion, how many electrons does the ion have? Nope.
0.
This is the loss of an electron. Oxidation is the loss of electrons. This has no electrons. None at all. So to describe this reaction, 2 electrons from the hydroxide reach out and make a new bond to that hydrogen. The electrons in the new bond both used to belong to the oxygen. So we can account for all of the electrons, and when this bond is made, it just looks like a covalent bond to me. It's 2 electrons shared between 2 atoms. Okay. So this looks really new, but it's always been there. And it turns out that this is the basis. Base sees acid, base reaches out and neutralizes acid. We're going to do this thousands of times on the board in organic chemistry. 2 semesters of organic chemistry, of following the arrows, and the arrow always starts at the base and always ends at the acid. Always starts where you have lots of electrons, always goes to where you have less electrons.
Can I ask what that circle is?
So this, what I was doing is saying that the dark dot originally belonged to the hydrogen. All the X's, there are 6 of them, originally belonged to the oxygen. And then that other one, that other circle, it's another electron, It's from somewhere else. It's the one that's responsible for giving the hydroxide its negative. It's an external electron. It came from somewhere. It came from the sodium. If this is sodium hydroxide, it came from the sodium. Okay, and this has no electrons at all.
What is the external electron?
Mm-hmm. All right, let's apply this and see if we can solve this problem. The charge on that oxygen, this one at the bottom, is its valency minus the number of electrons not involved in bonding minus the number of bonds. Go ahead.
Last time, I thought it was plus.
So what I did last time was did that.
Oh, and it gets distributed. Oh, got you. Thank you.
I think it's easy. But good. Well spotted. Okay, what's the valency of the oxygen? It's its group number 8.
No group number.
Helium, neon, argon, krypton, xenon, and radon have the group number of 8. 6. Oxygen is in group 6. How many electrons are not involved in the bonding? Is this electron bonding to that nitrogen? Is this electron bonding to that nitrogen? So you might say that this electron is not involved in the bonding. 4. 1, 2, 3, 4. They don't have to be in lone pairs. I think, yes, Monday I wrote down on the board number of electrons in non-bonding or number of electrons in lone pairs. They don't have to be. They just have to not be involved in the bonding. Minus, how many bonds do we have between the oxygen and nitrogen? So this oxygen is holding on to 2 bonds. So 6 minus 4 minus 2. There is no charge on that oxygen. Were we expecting a charge on an oxygen that has 2 bonds? No. No, we weren't. Okay. Let's do this oxygen. What's that oxygen's valency? 6. Yeah, we better not be different than the other oxygen. How many electrons are not involved in holding the oxygen onto that nitrogen? I count 6. And then how many bonds are there from that oxygen? That oxygen is bonded to this nitrogen. 1 time. Six minus 1 is minus 1. Were we expecting a charge on an oxygen that only has 1 bond? Yes. Yes, we were. An oxygen that only holds 1 bond
is usually associated with a negative charge. Okay? When oxygen has 2 bonds, no charge. When oxygen has 1 bond, negative charge. When oxygen has 3 bonds, positive charge. Okay. This is NO2. It is nitrogen dioxide. It is not NO2 minus, the nitrite ion. It is not NO2 plus, the nitrosonium ion. It's NO2. So, is there another charge in this molecule somewhere? Yeah. What's it going to be? It's going to be a +1. Because right now I have a 0 and a -1, so I've got a -1 in here somewhere. There has to be a +1 in here as well to make it all cancel out so that there's no charge left on this thing. Okay? Let's go figure. Mabel, did you have a question?
The rules that you're talking about for oxygen with valency, can that be also applied to all the other elements or only oxygen?
Kind of, sort of. The best, because we're talking about covalent bonds to oxygen there. So it really is best for that top right part of the periodic table. So we can do it for nitrogens and oxygens and carbons and phosphoruses and sulfurs. Yeah.
What's the valency of nitrogen? 5. It's in group 5.
How many electrons does it have that are not involved in bonding?
Just that 1. That electron's involved in bonding, that electron's involved in bonding, these 2 electrons are involved in bonding. This one, it's an unpaired electron, that's a radical. Radicals are generally bad things. And then, how many bonds do I have?
3.
So 5 minus 1 minus 3 equals +1. So this is one representation of what nitrogen dioxide looks like. And then there's a whole section in our book that goes off on a tangent that says, how do we know which oxygen it is? How do we know which oxygen has that negative charge? And the answer is, we don't know, because they both end up taking it in turns. But the electrons shuffle in a process called resonance. They shuffle from one side to the other. I'm not going to talk too much about resonance, but what resonance does is it always stabilizes the energy of the molecule that you're looking at. The electrons are a target. The positive charge is a target. The negative charge is a target. And if you can move them around, you now have a moving target, which means that they are more stable. Okay? All right. So formal charge is a thing. You will be asked a little bit about it. This was kind of the most difficult one that you can possibly find. So if you can do this, seriously, if you can do this one, you can do them all. This is a difficult example. Questions on that? Okay. All right. Now, oh, there you go. Section 8.6 in the book, resonance.
And it does 1, 2, 3, 3.5 pages. Then it talks about odd numbers of electrons. Oh, and then bond strength. I want to give you guys a very simple example. I think I'm going to use the one that's in the book. Okay. Let's talk about reactions. Well, we're still in the world of covalent bonding.
Let's talk about reactions.
It's been a few minutes since we've seen reactions, so it's worthwhile going back and revisiting. If we think about reactions that are covalent, not ionic, the deepest that we looked at chemical reactions previously was acids and bases, where we were in the ionic world, that a base, sodium hydroxide, and an acid, hydrochloric acid, put into solution, and they split apart, they dissociated into all sorts of things, but ultimately the hydroxide met the hydronium and made water, and that was the net ionic equation. Okay. For covalent, we're going to be able to do something a little bit additional. The enthalpy of the reaction, which again really is the enthalpy change for a reaction. We don't ever talk about enthalpies as being just the real number. But the enthalpy for the enthalpy change for a reaction is the combined bond energies that we could call bond enthalpies of all of the bonds that you have broken and all of the bonds that you have made. So the enthalpy change for a reaction is that symbol. What did that symbol mean? That's the sum. And in mathematics, what is a sum? You just add all the numbers together. That's what a sum is. We're going to add all of the numbers together of all of the bond energies. Do we actually call them bond enthalpies in this book? Our book is calling them bond enthalpies, and why not? Because that's what they are.
I'm just used to them being called bond energies.
You figure out how many bonds did you break? And then you look at what kind of bond did I just break? Where are you going to find that? It's in an appendix in the textbook. They're all written down. This is not stuff that you, as a 21st century student, have to figure out. This is something that the 18th century and the 19th century people did. They've already done this work. You don't have to repeat it. add together all the enthalpies of the bonds that have been broken, and then subtract from that all of the enthalpies of the bonds being made. Okay. Remember we said at the very beginning of this chapter that enthalpy is something that we associate with heat. Heat is something that we associate with kinetic energy. The potential energy in chemistry comes from storing the energy in chemical bonds. So typically, when we break bonds, we're doing something different to the energy than we do when we make them. When we make bonds, do you think we're storing energy or releasing energy? Yeah, I think that when you make bonds, you're more likely to be storing energy, and that when you break bonds, you are more likely to be releasing it. Does that mean that breaking bonds is going to be endothermic or exothermic? Exo. Largely. There's always an exception. But yeah, you break a bond, you will be releasing the energy that is in that bond. Okay. Let's give you an example. And I'm just going to use the one in the book because it doesn't have lots of atoms in it.
Plus, I'm doing this exact same I did this exact same reaction in my organic chemistry class on Monday. This is methane. It is a hydrocarbon. It is natural gas.
It's in the fossil record.
And this is chlorine gas. It is a homonuclear diatomic molecule made of 2 chlorine atoms. Both methane and chlorine are gases, not that that matters. I am going to switch some things around.
Hydrogen is in group 1 on the periodic table. What group is chlorine in? Yeah. How many bonds does hydrogen always make? 1. How many bonds does chlorine always make? 1. Which kind of gives us the sense that chlorine and hydrogen might be interchangeable.
I'm going to take one of the hydrogens and replace it
with a chlorine.
This is now called chloromethane. And
this only gets to be hydrochloric acid. You might say, well, that's HCl, that's hydrochloric acid. It only gets to be HCl, hydrochloric acid, when it's dissolved in water. When it's still a gas,
it's called hydrogen chloride, which is the wrong name
because "ide" means ionic, and hydrogen chloride is definitely covalent. Okay.
So, in order to get from here to there, I've had to move a few things around. I have broken that bond. And I have broken that bond. This part stays intact.
The carbon holding on to 3 hydrogens is still there. But everything else has changed. I have made that bond.
And
I have made that bond. So at some point, we now need a table of bond enthalpies. And there's one in the textbook on page 330. And without looking, I'm fairly certain that there is an appendix as well. The last big enthalpy table was Appendix C. Let's see if there's another appendix right behind it. Not quite. Unless it's B. No, no. There's no appendix, just the table in the chapter. Okay, bond enthalpies. So I have to look in this table and find some values. It says that a chlorine to chlorine bond has a bond enthalpy, it's in blue, of 242. This is going to be in kilojoules per mole. There you go. I also have to look up the carbon to hydrogen. That's the other bond that I've broken. A carbon to hydrogen bond is worth 413 kilojoules per mole. I next need to look up a carbon to chlorine bond enthalpy, which is 328 kilojoules per mole, and a hydrogen chlorine bond enthalpy, which is 200 kilojoules per mole. Okay. Here's what I want to know. I want to know what the enthalpy change for that reaction is. Go find it. Don't have to do it entirely on your own. Have somebody check your work. A question like this on a test is going to come with a follow-up question.
I got 127.
One. Let me look at what the actual number is. Okay.
Was I on?
I think so. This question is going to come with a follow-up that kind of says, comment on the magnitude of your value. Meaning, is this a big number or a little number? Or more importantly, or as importantly, because this is an enthalpy change, you have a positive number or a negative number. Enthalpy changes can be positive. Negative. And they can also be negative. If you get a negative value, what does that mean? It's exothermic, which means what? It's giving out heat to its environment. Heating up the environment, it is releasing its heat. Okay, do we have numbers?
-127.
Okay, we have another number.
4528 -600.
Really? Let's do it. Going to add up all the bond enthalpies that were broken, and then I'm going to subtract from it all the bond enthalpies that were made.
Shouldn't the answer be positive?
We'll find out.
But why does, I guess it's different than when we're doing it. I don't know, never mind.
So the last time,
In our other notes, when we did it, it was flipped.
Yes.
Okay, so this is different.
yes,
Okay,
this one is easier.
clearly, yeah.
Yes, because you can just slot the blue numbers where the blue numbers go and the green numbers where the green numbers go. The last time we did this, when we were looking at standard enthalpies of formation, giving us an enthalpy of reaction, we did enthalpies of products minus enthalpies of reactants. So we had to write everything out and then flip those numbers. This one is broken, formed, and because we always write the reactants on the left, we're always going to have the bonds broken be on the left and the bonds formed on the right. I'm going to give you another minute. Find me a number.
229, positive 229.
I'm going to give you a minute to find another number. I haven't heard the right number yet.
That was incorrect.
I'm going to give you a minute to find another number.
Right, okay, then I'll take that as a yes.
Yeah, so this one logically is easier than the last time we did a enthalpy calculation. Gonna need 3 pens. So what's the number?
1,183 kilojoules per mole.
Are we just adding everything?
Oh, shit, that's. Darn it.
Don't use the brown word.
Yes. I wrote the subtraction down too.
Are we sure? Did I? Okay, so now let me check. Did I write a wrong number on the board? 413, 242, 328. Oh, hold on. Did I use a wrong number? H to CL. Oh. H to CL. Where did I get my 200 from? That is odd. That is odd. That is odd. Yep. Yep, I transcribed the number wrong from the table. The H to CL value isn't 200. That's why that number is 431.
Okay.
Okay, do it again. Sorry. I don't even know where I got the other number from. It's not next to, so HCl,
Is that the final answer?
CCl. Well, the final answer isn't on the board yet.
Well, I mean, for the
Mm-hmm.
related data.
Mm-hmm. That is kind of odd. Well, all right, what's our number now? Okay, what's our number now? Still not right.
Is it really?
The book says negative 107. So that doesn't work, right? Oh, no, no. I might be having a stroke. Negative 104. There you go. Ah, okay. Monday, right? The enthalpy change for this reaction, negative, what does the negative mean? Exothermic. What does 104 mean? I don't know. Bigger than 100, smaller than 200. It's kind of a very measurable number. What's my units? Just kilojoules, not kilojoules per mole, because we're describing a reaction. We use kilojoules per mole to describe a specific quantity attached to a specific molecule. When it describes an overall reaction, we just leave it in kilojoules. All right.
Do we write the delta H, or the enthalpy of, like you said, shorthand for enthalpy of reaction? So that would actually be delta H R.
So that kind of mops up the remaining topic in this chapter. What comes next is gases, which is a whole nother thing to itself. We'll start those on Friday, but it will not be part of exam 3. Okay? So the next exam is covalent bonding, shapes of bonding, and then a couple of these little tag-on exercises about formal charge and about bond enthalpy. I will see you Friday. Oh, absolutely. Yes, I'm not going to make you memorize constants or anything. You will always be given a table. Yes.